Hello, I welcome you all to your own channel MSK Learning. Now in this video we are going to solve one problem which is related to the reheating and regenerations. So in the previous video we already discussed one problem which is related to the regeneration. So regeneration, reheating and intercooling, these are the method by which you can improve the performance of a gas turbine plant, right? So but also you know that the intercooling and reheating will be give you the better efficiency only when you can combine these method with the regeneration. So this is the one combinations of a reheating as well as the regeneration. So the problem is on the screen. Let's see that. In a gas turbine plant of 6 megawatt capacity, air enters the compressor at 100 kilopascal 300 Kelvin and is compressed to a pressure of 600 kilopascal. Means that one plant is there whose capacity is 6 megawatt, and the air which is entering into the compressor, its pressure is 100 kilopascal and temperature is 300 Kelvin. When it is compressed in a compressor, the pressure is become 600 kilopascal in a single stage compressor. So the temperature at inlet to first turbine is 1000 Kelvin. The expansion takes place in two stages. Means as you are reheating, so we are doing expanding the gases in two stages, like in high pressure turbine, in the low pressure turbine. So high pressure inlet temperature is the 1000 Kelvin is given. Now with the reheat of to 1000 Kelvin, means in low pressure turbine also the entering temperature of turbine is 1000 Kelvin only. The isentropic efficiency of compression is 80%, compressor efficiency is 0.8, and that of both turbine, means high pressure and low pressure turbine, is 85%. A regenerator having an effectiveness of 0.72. So effectiveness of a regenerator is given 0.72, is incorporated in the cycle to heat the compressed air before entering into the combustion chamber. So the calorific values of fuel is 18,500 kilojoule per kg. Determine first one, air fuel ratio entering the first turbine, second is the thermal efficiency of the cycle, and the third is air supply to plant. For air, a specific heat is given 1 kilojoule per kg Kelvin and the adiabatic index is 1.4. For gases, the specific index is specific constant is 1.15 and the gamma is 1.34. So this is what you can write down this question, right, as I dictated you. Now I'll tell you in short, in brief, that you have a one gas turbine plant which works on a combination of reheating and the regeneration. So whatever the air is entering into the turbine compressor, its pressure and temperature is 100 kilopascal and 300 Kelvin. After compression, the pressure has become 600 kilopascal. The two-stage expansion we are using, that is reheating. So air means air entering into the high pressure turbine and low pressure turbine, temperature is 1000 Kelvin. The efficiency of a compressor is 80%, and the turbine efficiency for both, that is high pressure and low pressure turbine efficiency, is 85%. There are the regenerator is incorporated with this plant, okay, whose effectiveness of a heat exchanger is 0.72. You have to find out the thermal efficiency. Second, you need to find out the air entering into the air fuel ratio, and third you have to find out air supply to the plant, right? And the plant capacity, that power of the plant is given 6 megawatt, right? So for better understanding, I always say that you need to draw the schematic layout as well as the TS diagram. That TS diagram is must and should, but a schematic layout is not necessary. But if you draw, you can picturize them and you can easily understand the things. So first of all, what I'll do, that I'll draw the TS diagram for the given problem. So here you can go like this, that let's say this is your high pressure, that is compressor, right? This is your compressor, and then it is one heat exchanger. First combustion chamber is this one, right? And then it will be enter into the high pressure turbine, right? And then it further it enter into the low pressure turbine. Sorry, means here you have again combustion chamber is there, you can arrange here combustion chamber, right? And then it enter into the low pressure turbine, right? And from here it will leave and enter into the, means here it will be heat exchanger, which is used to heat the air which is coming from the compressor and leaving entering into the combustion chamber, right? So if I show you, this is the compressor. Let's say this is C, combustion chamber 1, CC1. It is the high pressure turbine, HPT. This is your CC2, right? This is the low pressure turbine, and these are the direction, that is first air is entering into the combustion compressor. It will be like this, it is like this, it is like this, this, and this is again this one, and this is, right? So now if I say you that this is the one, right? That is the inlet of the compressor, exit of the compressor. This is the inlet of the combustion chamber, but it is exit of the heat exchanger. So here you have a 4, and this is the exit of the high pressure turbine, 5, and this is the entrance of the low pressure turbine, which is 6, and this is the leaving, which is the 7, you can say, right? Now so this is what you have. So you know, in high reheating, whatever the two turbine we are using, that is high pressure turbine and low pressure turbine. So whatever the work we are developing in high pressure turbine, the whole work we supply to the compressor, so that the compressor can run, right? Why? Because compressor is a work input device. So we have to couple them, this high pressure turbine and the compressor. It means that whatever the work we are getting from the high pressure turbine, the whole work we supply to the compressor, right? Now, and this low pressure turbine is responsible for the power generation. So here you can say this is the turbine output, right? Now that this output will give you the plant efficiency. Now we can draw the TS diagram, that is you must have to draw the TS diagram in your exams, right? But a schematic diagram, it is additional. If you draw, it is good. If you don't, there is no problem, right? So now we are drawing the temperature versus entropy diagram. So here itself you will go in a simple manner. This is your temperature on y-axis and the entropy on x-axis, right? So two pressure line will take. This is high pressure line and this is the low pressure line, right? The two stages we are using in expansion side. So we have stages we provided, right? Two process we need to execute, isentropic and the reversible adiabatic. Isentropic means what? This is ideal, and reversible adiabatic means actual. So both process I will show you. First I will draw the process for the isentropic, means for ideal expansion and compression. So let's say this is 1 to 2. You are compressing the air in a compressor, okay? And then what you are doing, that here you have a, let's say this is the end of the combustion chamber 1, and then you are expanding this isentropically expansion 4 to 5. This will be your another combustion chamber, that is combustion chamber 2. This is the exit of the combustion chamber and the inlet of the turbine, right? So you can extend this line. So this is what, now this is the process for ideal process, means what? 1 to 2 isentropic compression. But if you look at here, if you look at this schematic layout, that is 1 to 2 is compression. So 1 to 2 is a compression, that's fine. 2 to 3 means what? There is a heat exchanger is there, right? And then 3 to 4 is this one. So it means that this exit of the entrance of the exit of the combustion chamber, I will write down 4. This is 5, right? And this is the 6, right? So this is your 7. These are the ideal process. Now I'll show you where it is 3. 3 will come. So first of all, we have to show the adiabatic. So 1 to 2 dash is the reversible adiabatic compression. Again heat supplied, and 4 to 5 dash is the reversible adiabatic expansion in a high pressure turbine, and 6 to 7 dash is the reversible adiabatic expansion in a low pressure turbine, right? Now then here you have a, suppose here you have a heat exchanger. Why? Because 1 2 to 3 you are adding the heat, right? In a heat exchanger, then the air is entered into the combustion chamber. It means that this 3 will come here, right? And then this is what you have a 7. If you draw like this, so this line will goes, is it or not? So this will be your 7. That we need not to write, but I'll show you just additionally right now. So when you find out the effectiveness is what? Actual temperature rise by maximum possible rise temperature. So actual temperature rise is what? 3 to 2 dash, means 3 to 2 dash, and maximum possible rise is what? Maximum possible rise is nothing but the 7 to 3. Is it or not? Now, so then we can say that that inlet temperature pressure inlet turbine temperature, temperature for low pressure is also given, but we don't have a exit temperature of a compressor, exit temperature of a high pressure turbine, and the exit temperature of a low pressure turbine is not given. First of all, we need to find out the temperature at the salient point, right, and then we can impose these values into the empirical relation. We'll get that things. So it's very easy. Now first of all, what I'll do, well, I'll calculate the 2 and 2 dash. For that we'll use the 1 to 2 process. So now this is what you can start solving. 1 to 2 dash. Sorry, I forgot to write down the given data right now. So given data I'll write down here. So first of all, you need to write down the given data. That will be very easy. Wait, I just tell you the question and then you can see. In a gas turbine plant, the power is given, that here you can write that given, this you got given data, right. The power of capacity of a plant is, power is equal to 6 megawatt, right, 6 megawatt. So I'll take it, convert this into Kelvin, that will become 6000 kilo, so kilowatt, right. Air enter into the compressor at a pressure of P1 is equal to 100 kilopascal. So as I have taken the power in kilo, so we need not to convert this. So temperature is what? Inlet temperature is 300 Kelvin, right. Then you have a leaving temperature, means compressed air pressure is what? P2 is equal to 600 kilopascal. Very carefully you'll see. And then what is that? Here itself I am writing, right, that is the air inlet temperature of the turbine. So turbine temperature is what? T4, right. So T4 you can say here, that you come and you can say T4 is equal to 1000 Kelvin, 1000 Kelvin. And again for low pressure turbine also, the inlet temperature is 1000 Kelvin. So low pressure turbine is this one. So T6 is also given, right. So you can say T6 is equal to 1000 Kelvin. The compressor efficiency neta C, isentropic compressor efficiency is given, which is 80%, means 0.8. Turbine efficiency for high pressure turbine, HPT is for high pressure, and the neta LPT, low pressure turbine, is 85, means 0.85, right. The effectiveness of a heat exchanger is given, epsilon is equal to 0.72. These are the data is given, and also the properties of air is given. Properties of air, in some time they won't give, but if you have to remember that a specific heat for air is equal to 1 kilojoule per kg Kelvin, and the gamma is given 1.4. This is for air, right. And for gas, CPG is equal to 1.15 kilojoule per kg Kelvin, and the gamma is equal to 1.34. This is for air, right, and this is for gases, means hot gases, right now. So these are the data is given to you. We have collected the data. Now we can impose the relations, right. So first of all, as I told you, we are going to find out this temperature and this temperature. Later on we'll find 5 and 5 dash, 7 and 7 dash, and then we execute the problem. So let's do that. So first of all, without wasting the time, I'll write down the 1 to 2 process. 1 to 2 process, right. 1 to 2 process is what? T2 by T1 is equal to P2 by P1 whole power gamma minus 1 by gamma. This is air, so T2 is equal to T1 times of P2 is what? 600 kilopascal by 100 kilopascal. Gamma is 1.4 minus 1 by 1.4. T1 is given 300. So when you substitute 300 into 600 by 100 whole power 0.4 by 1.4. So you will get the T2, right. So on calculation, we will get the T2 value as 500.55 Kelvin. 500.55 Kelvin. As I told you always, that you check whether this calculation are correct or not. There is a 0.1% chances that you get the error right now. So T2 we got. Now we need to find out the T2 dash. This is the ideal temperature at the end of the compression we got. Now we need to find out the actual temperature at the end of the compressor. So for that we'll use the compressor efficiency. So now you can say that compressor efficiency, right? Compressor efficiency. So what is the compressor efficiency? Neta C is equal to isentropic work by actual work. Isentropic work upon actual work by actual. So what is the isentropic work? Means T21 T2 minus T1 by actual is T2 dash minus T1, that is equal to neta C. So when you cross multiply, you'll get the, directly I'm writing T2 dash is equal to T2 minus T1 by compressor efficiency plus T1, right? So all the values you have, substitute and get that answer. T2 dash, T2 is what? That you just now you find out 500.55. So this is 500.55 minus 300 by compressor efficiency is 80%, 0.8 plus 300. So actual temperature you got T2 dash, right? On calculation you will get the 550.68 Kelvin. So actual temperature is more than the ideal temperature for compressor. Compressor efficiency will, compressor temperature will got. It means that if I show you that this is the, at this point we got the temperature 2 and 2 dash we got. Now we need to find out the 5 and 5 dash. So for that we can use the turbine. Before that we can also calculate the work input of a compressor. So here only you can find. Why work input I am telling? Why? Because compressor is a power input device, right? Compressor won't produce the power, it takes the power, right? So we can say the work input to compressor, work input to compressor, right? So work input to compressor is what? That is W in is equal to Cp. Actually MCP, M is 1 kilogram we are taking. So from where to where? Actual work we are calculating, right? So T2 dash minus T1. Here you can write better that it is the actual. Okay na? So actual compressor work is what? Cp is 1. T2 dash you have calculated 550.68 minus 300. So on calculation we will get the work input is 250.68 kilojoule per kg. So you got the work input. Work input we calculated. Sorry. So work input is this one, right? So work input we calculated is 250.68. Now what we need to do? We find out the temperature and pressure for turbine, right? That is for high pressure turbine and low pressure turbine. So for that I'll go to the next, that you can see here that we have completed the whole calculation for the compressor. Now come to the high pressure turbine. So 4 to 5 you can say. So before that we need to find out the P4, right? So why? Because this pressure, let's see that this pressure you don't know, right? 2 and 4 is 600, 1 and 7 is 100, but 5 you don't know. So 5 we need to find out. So 5 is what? 5 is equal to, P5 is equal to P2 into P1, right? Why? Because it is the perfect pressure division, right? So you can say the, so you have a, here you can write for perfect pressure division, the intermediate pressure for perfect pressure division, right? This is pressure, PR is the pressure. For perfect pressure division, the intermediate pressure, right? Intermediate pressure means what? That P5 is equal to root over of P1 into P2. This relation you know from the air compressor, right? That how to find out the intermediate pressure in case of the intercooling actually, right now. So now P1 is what? 100 kilopascal and this is the 600 kilopascal, whose values will got the 245 kilopascal. It means P5 we got. P5 is equal to what? 245 kilopascal. Now you can execute the process in turbine, right? So for turbine it is what? So turbine you can say 3 to 4 process, 4 to 5 process, right? 4 to 5 process. So what is that? T4 by T5 is equal to P4 by P5 whole power gamma minus 1 by gamma. But if I show you that P4 is what? That P4 is nothing but your P2. Why? Because it is constant pressure line, right? So which is the 600 kilopascal, but P5 we calculated 245, right now. So now we need to find out the T5. So T5 is equal to what? T5 is equal to T4 by P4 upon P5 whole power gamma minus 1 by gamma. So when you substitute these values, that is you have T4 is 1000 kilo Kelvin, 1000 Kelvin by P4 is what? 600 by 245 whole power gamma minus 1 by gamma. Which gamma you take? That is 1.4. So this is the 0.4 by 1.4, right? Now on calculation you will get the values. Sorry, this is not 0.4. Actually for the gases it is 1.34 is given, right? So this will be 0.34 and this is the 1.34. Make a correction, this is 0.34. Why? Because gamma is 1.34. You will take 1.34 minus 1 is 0.34. So do the calculation. So T5 you will get, that is exit temperature of the turbine, which will be 796.7 Kelvin. So first high pressure turbine ideal temperature we got at the end of the expansion. Now you need to find out the actual temperature. So for that actual temperature we will use the turbine efficiency. Turbine efficiency is what? Actual work by isentropic work. It's just reverse of the compressor, right? So now you can say, just hold on. See, this is sometimes it's, so now you can say the turbine efficiency. Okay, so turbine efficiency is what? That neta T is equal to actual work by isentropic work, right? By isentropic work, right? So turbine work is what? That neta T is equal to actual work means what? T4 minus T5 dash upon T4 minus T5, right? So this is your turbine efficiency. We need to find out the T5 dash. So what is that? The T5 dash is equal to we need to find T5 dash. So T5 dash is equal to T4 minus neta turbine times of T4 minus T5. Substitute you all the values you have. T4 is given 1000 in the question, turbine efficiency is 85, right? T4 you have again 1000 and T5 just now you calculated, which is the 796.7, right? So on calculation you will get the T5 dash, that T5 dash is equal to 827.2 Kelvin, right? Why? Because if I do the calculation right here, it takes time right now, so the video will be very longer, right? So the duration of the class will be more, so that's why I am directly writing the data. Actually it is calculated, so for your satisfaction you need to do the calculation. Okay, so now we got the actual temperature at the exit of that high pressure turbine and the ideal temperature at the high pressure turbine. Now we have to move to the low pressure turbine. So if you look at the turbine efficiency for the high pressure and low pressure turbine are same. It means that the exit temperature for a high pressure turbine and for low pressure turbine should be equal. So now you can write that right. So now you can write here so you can say that the temperature high pressure turbine efficiency, you can make a note that since efficiency of high pressure turbine is equal to efficiency of low pressure turbine, therefore what? The T5 dash is equal to T7 dash is equal to how much? That same 827.2 Kelvin, right? So these are the things we got. Right, so let me show you that this is what this is. this is your high pressure turbine and this is the low pressure turbine. The efficiency for both the turbine is same, so this temperature and this temperature will also same, right? Now then we need to find out one more temperature, that is this temperature, right? That is the means temperature which is entering into the combustion chamber, right, after compressor. Why? Because here you have a regenerator is there, right? So if you look at it, this is the heat exchanger. It means that you are heating this air, whatever the air is coming from the compressor, you are heating here, right? So this temperature and this temperature is not same. So when you find out the heat supplied, you need to use from here to here, not from here to here, right? Now, so that's why we need to find out that this temperature, and this temperature we can calculate by using the effectiveness, right? So now you can see that effectiveness of heat exchanger. So you can write the effectiveness of heat exchanger, right? So effectiveness of heat exchanger is what? If you remember, the actual temperature rise by maximum possible rise in temperature, right? Rise in temperature, or you can say effectiveness is equal to effectiveness is equal to what? Delta T of actual by delta T of maximum. So what is that effectiveness? That you can say from where to where. I'll show you. Actual temperature rise is what? Actual temperature rise is 3 to 2, and maximum possible rise is what? T7 dash to T2, right? Now so you can say T3 minus T2 dash by T7 dash minus T2, right? Okay, so effectiveness is what? 0.72. T3 we have to calculate, T3. T2 dash we calculated already, which is your how much? T2 dash is 550.68. So 550.68 by T7 dash we already got, that is 827.2. This is 827.2. So 827.2 minus T2 is 500.55. I think this is also T2 dash only, right? Now so this is also T2 dash. So T2 dash means what? 550.68. Make a correction, T2 dash, right? 550.68. So now when you simplify, you will get the T3 value is you got that 749 Kelvin, right? So all the temperature we got, even the regenerator temperature also we got, right? So first of all we need to find out the air fuel ratio. How much air is there? You consider that 1 kilogram of air is entering to the compressor, turbine and combustion chamber, right? So in combustion chamber 1 kilogram of air is entering. So for that, first of all you should know that how much fuel is entered. So fuel, how can you use that? By energy balance. That mass, here I can see you that heat supplied is equal to what? Mf into Cv is equal to, from where to where? You are supplying the heat from T3 to 7, is it or not? Sorry, that 4 to 7. So you can write that first you have to find out the air, first bit, air fuel ratio, right? So air fuel ratio, how? Air fuel ratio supplied to the high pressure turbine, actually supplied to high pressure turbine. HPT means high pressure turbine. So how you can say, let, that is the MF1 is the mass of fuel entering mass of fuel enter into the main combustion chamber, right? Into combustion chamber 1. So means MF1 amount of fuel is entering into the combustion chamber 1. So what is that energy balance if you say? So MF1 into calorific value, heat supplied is this one, that is equal to what? That is equal to 1 plus mf1. 1 is what? For air plus fuel, right? That means combustion is takes place from where to where? From 4 to 7. So you can say T4 minus T7, right? T4 minus T7. So when you simplify, that is mf1 you need to find into calorific values is what? 18,500. It is given in the question. 1 plus mf1 and T4 dash, that inlet temperature of turbine, which is 1000, minus T7. T7 you just now you calculated, which is the 749, right? So 749. How much you'll get? That air fuel ratio, fuel value we will get, that is mf1 is equal to 0.0137 kilogram, sorry, 0.0137 kilogram per kilogram of air, right? Means for 1 kilogram of air, 0.0137 kilogram of fuel is entering, right? So when I find out this, means when you have to calculate the air fuel ratio. So for air fuel ratio, what we can do, that so for air fuel ratio you can say that here air fuel ratio. What is the air fuel ratio? That is equal to mass of air by mass of fuel. mf1 we can say better, that 1 by 0.0137. So this is your answer, that is 72.9. This much of air fuel ratio is entering. So first answer we got, right? Now second, you have to find out the thermal efficiency of the cycle. So thermal efficiency is what? Net work by heat supply. Net work means what? Turbine work minus compressor work, right? And turbine is 2 times we are doing the work, that is in high pressure turbine as well as in the low pressure turbine. So first of all, you need to find out that mass of fuel enter into the second combustion chamber, that is reheater, right? So then only we can get the work output. So here you can say next we have to find out the thermal efficiency, right? Thermal efficiency. So how can we get output by heat supplied? So first of all, we can say the consider mf2 is additional fuel added in a reheater. Means what? That again you are reheating. So for reheating you have to use the fuel. So how much fuel you are using, that we have to see. So mf2 into calorific values is equal to 1 plus mass of fuel in first combustion chamber plus mass of fuel added in reheater into from where to where you are using that, from T5 to, show me, wait. So T5 to T7 dash, right now. So you can say the T5 dash to T7 dash. So this is what? T5 dash minus T7 dash. This is the second reheater. So now you can see mf2 you have to calculate. So mf2 into calorific values will same 18,500 is equal to 1 plus mf1 we already calculated, which is 0.0137 plus mf2, right, into T5 dash. T5 dash is nothing but a 1000 minus, and this T7 dash we calculated, which is the 827, right? Point something is there. So 827.2, right? 827.2. So when you simplify this, you will get the mf2. So mass of fuel, that is which is entering, means used in a second reheater or second combustion chamber, which is nothing but the 0.011 kilogram per kilogram of air, right? So this much of fuel we are using in the reheater, which is very means it is near about the first combustion chamber only. Now we need to find out the work output, right? So work output, how can you find that work output? So work output means high pressure turbine and low pressure turbine. So you can say that is work out is equal to W in high pressure turbine plus W in the low pressure turbine. So high pressure turbine, I'll show you this with the schematic layout. That is, high pressure turbine is what? That you can see from 4 to 5 dash plus 5 dash to 7 dash. Means in this you are using the fuel 1, and in this you are using the MF1 and MF2. Understood? Now, so you can see here that high pressure turbine work is what? 1 plus MF1 means what? That is 1 kilogram of air, and MF some fuel is used, and then you have a specific heat, that is CPG, and the temperature is what? T4 minus T5 dash, right? And then we are using this as a what? Plus 1 plus MF1 plus MF2, means this is the first combustion chamber and second combustion chamber, into CPG, right? This is continuation into what? That 6 to 7, right now. So this is what you have, a T6 minus T7 dash. Okay, so here it is not 5 dash, actually it is 6 to 7 dash, right? 6 to 7, make a correction. So now 6 to 7, we got this 6 to 7 dash. So now you have a 1, MF1 is there 0.011, CPG is 1.15, T4 you know 1000, T5 dash we calculated, which is 827.2, MF1 you have same 0.011, 0.0137, 1.15, this is 1000, and this is the 827.2. So on calculation, when you substitute this value, as I told you, you will get the work output is 404.76 kilojoule per kg. All the data you have, right? So you got the work output right now, that is work output you got, which is 404.76. Now you need to find out the net work. Net work is what? Work output minus input work. That input is what? That, as you remember, that whatever the work is produced in high pressure turbine, the sole work we are supplying to the compressor. So means you need to subtract from this work, compressor work you have to substitute, then you will get the net output, right? Now you can say just we are almost near to complete, right? So now you can say the net work, that is net work, right? So net work is what? W net is equal to work output minus work in. So work output is what? That which we have calculated now, 404.95, minus input work is your compressor work, right? So compressor work is how much? 250.68. We have calculated at the beginning itself, 250.68. Why? Because we have started from the compressor itself. So this will be 154.08 kilojoule per kilogram of air, right? So this is W net you calculated, kilojoule per kilogram, right? So net work we got. Now we need to find out the heat supplied. Where you are supplying the heat? So heat you are supplying, actually that is same, you can say MF into CV, right? Mass of fuel into calorific value. So you can say heat input, that is heat supplied. Why? Because you already calculated the mass of fuel. So heat Q in, I can say. So what is that? MF, mass of fuel used in combustion chamber 1 plus mass of fuel used in the reheater into calorific value, whatever the fuel you are using, whose calorific value. So this is what? This you calculated 0.0132 plus 0.011, and calorific value is given 18,500. So when you simplify this, you will get the values as 456. Yes, let me check. I'll have confusion. So just hold on. 0.0132 plus 0.0. Sorry, 0.0. So this is the, is it correct? 0.0137 plus 0.011. Answer into 18,000. So you've got 456.95, right? So your heat supplied or heat input is 456.95 kilojoule per kilogram of air, right? So Q in you got, right? Now then we can simply find out the efficiency. So efficiency of plant is what? That you can say the thermal efficiency, right? So thermal efficiency is what? That neta TH is equal to W net by heat supplied, right? So W net is what? W net you have calculated here 154.08, and the heat supplied you calculated just now 456. Put this value, that is 154.08 upon 456.95, right? So this you got actually 0.337, which is nothing but the 33.7 percentage. So 33% you are getting the efficiency of your plant for this combination of regeneration and reheating at a given pressure and temperature. Right now means when the air is entering in a compressor at 100 kilopascal and 300 Kelvin, that means it's near about the atmospheric condition, right? And when you are using the combination of reheating and the regeneration, near about 30 to 35% efficiency you will get from the plant, right? Next you have to find out that mass of air supplied to the plant, means how much air is supplying in a plant, right? In terms of the second we can calculate. So for that power is given. You know the power is equal to what? Rate of capacity to do the work, we know the power, right? So whenever work we multiply, means work we have to so now wait, yes, so here itself you can see, wait, so now you need to find out the air supply to plant, right? Air supply to the plant. So for air supply plant we can use the power is equal to what? Mass of air circulated into work done, right? So mass of air into W net, right? So mass of air we have is what? Mass of air circulated is equal to this, which is given. Power is equal to 6000 kilowatt, that means 6000, and net work we have calculated, which is 154.08, right? So mass of air supplied to the plant we got, which is 38.95 kilogram per second. So it means what? That means 38.95, near about 39 kilogram of air is circulating in 1 second in a plant, right? Means this much of air is flowing in a plant in 1 second. So this is all about the today's class, right? In next class we will start the new chapter, that is the introduction of thermodynamics, right? So please do like, subscribe, comment and share this channel. Thank you.